Not so far.
So, yeah, that one. Dolomite. Wait, no, that's it.
It's pronounced Dolomite.
So all of you are signed up for the food trip, huh? No? Some of you are sitting in the class. And this is your daughter, John?
Yes, this is Elizabeth. This is daughter. One of the helpers who went to San Salvador.
So you tell me when we're ready to go, Jeff. It's almost 4. I'm gonna go. Is that quicker? I was hoping. This would show. Nobody's covered it. So she'll try and get in her seat. I was a new chat.
Yeah, some other.
I'll be.
Virtues other than.
Not really. No.
That was actually subpoena. Yeah, I didn't have a chance to get that.
Oh, you've been subpoenaed?
Yeah, let's start that rumor. If I'll get out of being here sooner than I.
Oh, another one. Oh, you're the best.
Is that a repeat?
No. No.
All the pictures look so beautiful.
So I'm sure they enhanced the video. Are you sure these are the actual colors of the rocks? I don't think they're actually that color. These are European colors, which are bright, vivid, don't match at all. Yeah. They always like to do that. Incompatible colors are possible.
Korea starts then. He has some birthdays.
Really? Who's got birthday today? Bonnie?
Yeah.
Anybody else? Well, since Scott is happy birthday?
Yeah.
You had a birthday, Saturday. Hey! 1 year older and I keep to. Happy birthday to you.
I only know that Bonnie.
Okay, now that the real teacher's here, let's get started.
And here's the roll, so you have to check your name off the roll in order to get credit for being here. And that I.
It's voice.
Well, I'm not sure what the
broadcast
are. I checked the name off, but I'm sure there's
Yeah.
Yeah, as long as you wear the microphone, it'll pick
We
you up
both
wherever you are.
welcome
So.
Scott here today to talk to us about the Dolomites. And I know that. Okay.
What's that?
Okay. All right, you guys. Thanks for the invitation to be here this afternoon. I'm envious that you get, most of you anyway, get to head off to Europe this summer. Are you going on the trip? No. Elizabeth.
Oh, yeah.
You're going too. Okay. Good.
It's not going, I'm not going.
Okay. Well, that'll be. So that's quite the daddy-daughter date. I love it.
This is my daughter Elizabeth. She will also be going on the trip, and you can use your influence to convince her to study geology.
Yeah.
And I have no influence.
All right. All right. Well, good. Glad to be here.
You'll get an A in every class. Who would get an A in every class as long as I share?
Okay, I've given you a few handouts just as sort of a summary of what we're going to go over, visual summary. The Dolomites, absolutely beautiful place. I've been there once. We were in more of the western part of it. I think you're going to be coming around the east side. But anyway, so what I'd like to do is sort of go through this quickly. Again, the Dolomites, the man, the mineral, the mountains, sort of in that order. The first two pretty quickly, and then spend most of the time looking at the geology of the Dolomites. Okay, so you can see it's a beautiful place. It's located in northwestern or northeastern Italy. The name of the mountain range derives from this gentleman, He was a French naturalist. You can see he lived from 1750 to 1801, so he didn't live very long. Got to his 51st birthday and died. But when he was a younger person, he went to the South Tyrol, to the southern calcareous Alps. And when he was there, he noticed a rock that looked like limestone, but when he put acid on it, it did not effervesce very much. So he was quite curious about it, collected some samples, sent it to a Swiss mineralogist by the name of de Saussure, Nicolas de Saussure. And in 1791, so this was in like 1790 when it was discovered, 1791, the Swiss mineralogist named this newly discovered mineral and named it after Dolomieu. So his real name, his complete name, here it says Déodat de Dolomieu. It's Dieudonné Sylvain Guy Tancredet de Grédet de Dolomieu was his name. So how would you like to just put "ite" on the end of that? That would be a mineral. So fortunately, anyway, so the mineral dolomite was discovered by him, was named by someone else in honor of him, and then the mountain range came to be known as the Dolomites.
You speak French?
Yeah.
Wow, that's very impressive pronunciation.
Yeah, okay.
I couldn't ever do that.
Yeah, thanks. Spent 2 years learning. This particular, you won't be in this place. This is in Cortina, a little town in the middle of the Dolomites. And my wife and I were taking an evening stroll, and there was this big slab of dolomite down in the square downtown, and it had this little plaque in honor of him. The mineral itself is a carbonate mineral. It's a double carbonate. You know, most calcium carbonate, calcite, aragonite is calcium carbonate, but dolomite is limestone that's gone bad. It's been invaded by magnesium-rich waters and replaces part of the calcium. So you get a CaMg, calcium magnesium carbonate. And sometimes you can preserve the structure of the original sedimentary rock pretty well. Other times that dolomitization can obscure it. And, you know, and if you're looking for oil reservoirs, I guess that can be okay. Good intercrystal porosity, for example, here. So here's thin section photomicro, and then a scanning electron photomicrograph of the mineral dolomite. The dolomite mineral that you see there with the blue in the background, this is from the early Triassic Sinbad limestone over in the San Rafael Swell. Same age as some of the beds, the age of the dolomites over there. So that's the man in the mineral. These are the mountains. So Venice is down here. And are you heading? You're heading to Venice through the Dolomites? I can't remember. Going up.
All the way around.
Look up around, then you come back down. All right. So this triangle right here is the South Tyrol. This is where the Dolomites are. The Austrian border is here. You probably come through Brenner Pass, and then I think you're going to work your way east of the Dolomites. I'm more familiar with this part of the Dolomites, but that's okay. So if let's zoom in on this area right here. This is the town of Bozen or Bolzano. And then you can see these snow-capped peaks. These are the high peaks, the craggy peaks of the Dolomites in snow here. And you can see that the range is really one of sort of blobs or patches of high mountains with valleys in between. And we'll talk a little bit about why that is, what that means geologically. So I think you're going to come down around this way in some fashion because you're going to go look at the dam that failed, right, and flooded. And that's down here, Longarone. So I think you'll be coming down the Cador Valley. And so you will see the Dolomites sort of from the north and from the east. This is Mount, however you pronounce it in Italian, But this is called the King of the Dolomites. So you'll be coming down the Cador Valley, and these are some of the types of views that you'll have in the area that you're in. And what you're looking at in the high peaks are Triassic carbonates, Triassic limestones that have been, by and large, replaced by dolomite. Let's see. But more generally about the Dolomites, it's hard to take a bad picture in the Dolomites, right? As long as you don't have it tilted or, have your thumb in the way. Beautiful green meadows and slopes giving way to craggy high peaks of limestone, dolomite, carbonate. Man, imagine trying to hike up through that. How about doing geology summer field camp here, mapping the dolomite? It'd be kind of cool, but after about 2 days, you'd be going, this sucks. Because it's straight down, and it's complex geology as well. And here's another view from up in the Dolomites, up in the rocks themselves. Rock climbing is a huge sport over in the Dolomites. So this was my first view of the Dolomites, and it was pretty. It was pretty exciting. It felt like a little school kid. Yeah, the Dolomites, driving, taking all these panoramic pictures, and times 10. Anyway, just absolutely gorgeous. Again, little villages, beautiful green tree-covered slopes giving rise to these huge, several thousand-foot high cliffs of carbonate rock. So here's the geological map that I handed out to you. So here's Bolzano over here. Here is the valley that you'll be coming through. So it's a fairly self-contained area. This geological map shows you what you would see in any of those areas. So up along the north end, in the brown basement rocks. The basement rocks here are Ordovician through lower Carboniferous beds that have been intruded and metamorphosed, turned into crystalline rocks during the Hercynian orogeny, which we call the Allegheny orogeny here on this side. So that's the basement rocks. Most of the rocks that you'll see in the Dolomites, the Triassic is the real story there, although the immediate underpinnings of that are these Permian rocks. You can see those in orange and red and yellow, and then the pinks and purples and light pinks are the outcrops of the actual Triassic rocks. And over there where the star just came up, that's probably where you will have your best view of the Dolomites. Structurally very complex. So here's Bolzano again, and here's the valley that you'll be in. This is a cross section essentially from north to south. And here are the Dolomites. You can see that they are on thrust sheets of the Alpine orogeny. They're in a broad synclinorium, and they've been moved as recently as the Neogene period. When did Mount Timpanogos get moved into its place? When did we have thrusting that we're familiar with here along the Wasatch Front? The severe orogeny, so Cretaceous. So this is much younger, compressional tectonics. So very complex, and fortunately we don't have to get too far into the structural weeds. There are some to get into if you're really interested in that. There are a number of great papers that I'd point you to. But most people work in the Dolomites to look at the sedimentology and mixed sedimentology structural or sedimentary tectonics. So here's where the dolomite, the rocks that we're going to be looking at, formed. So here's Pangaea, Panthalas Ocean, this broad embayment on the east side, what is called the Tethys Ocean. So back at the time, there were highlands to the northwest, ocean to the southeast, and sort of in between tectonically as well as depositionally, period of rifting, a couple different periods of rifting, and then deposition, sedimentary healing, and more rifting and more healing. So very complex interplay between structure and tectonics.
Calcite dolomite or heating?
Just forming a very complex topography, structural setting, and then filling all of that in with sediment, sort of resetting the clock and then, or resetting the table for more sedimentation. Okay. That should come out as we go on here. So here's the other handout I gave you. So here's the stratigraphy for the Dolomites. So here are the upper Paleozoic basement rocks from the Hercynian orogeny. A couple thousand feet of Permian rocks, several thousand feet of Triassic rocks, and then a little bit of Jurassic and Cretaceous. But it's mainly a story about Triassic.
You get granite from the Permian rock.
Yes. Yep. There are intrusives in there. Yep. So you'll see all these letters over here. And then here's the corresponding names. Now, to give you a little bit of perspective, since you are coming from Utah, I'm not sure when you last memorized all this series and stages of the Permian and Triassic. Probably not real recently. Last week, good. Okay, so here's Permian Triassic coming from the San Rafael Swell. The Permian out there is the Kaibab and White Rim, and a thing called the Black Box Dolomite. But those were all deposited during early Permian time. No rocks of late Permian, middle to late Permian. The Moenkopi Formation, I think you're fairly familiar with, was deposited during the earliest part of the Triassic. No middle Triassic. The Chinle is late Triassic. Okay. But these are the time terms or the stage names for the lower, middle, and upper, or early, middle, and late Triassic. And somewhere in your guidebook, you should probably have that, just so you can refer to it when you get over there. So whereas we have a fairly thin, fairly simple, straightforward package of Triassic rocks in Utah, although there is an unconformity here because of structural complications, so it's not all that straightforward. When you get to the Dolomites, you're going to have a much more complete and interesting package of rocks in the Triassic. Let's just go through some of these on that strat column, see what they're telling us about the history. This is a slide showing the Permian. So here are the basement rocks, and this is in the, just across that swatch in the Dolomites. How thick are the Permian rocks in the Dolomites? Can you read the scale there? 2 to 3 kilometers thick. And basically what was happening was there was some rifting going on, and that's what these sort of stair steps and faults are trying to show. So there's rifting going on, and lots of accommodations blocks drop down in. Sediment is pouring into these down-dropping blocks, and there was also a vast amount of volcanic activity associated with this rifting. So you have volcanics and volcaniclastic rocks 2 to 3 kilometers thick, filling in this structure. But by the time you get to the Val Gardena sandstone, at the top, you can see that things have pretty well filled, and that's sort of what I mean by healing, where you start up with all this structural stuff going on, then you fill the accommodation, you're back to sort of a flat surface. So that's what the Permian looks like, and you probably won't see a lot of it. You may see some in the valley where you're headed, but again, I haven't been over there, so I'm not sure. Here's what it looks like on the west side. So you have this, as you drive through, you just have these beautiful, again, tree and grass-covered hillsides. These are all grape arbors, though. So for some reason, in that part, I don't know if it's the soil or just the climate, but the locals have taken great advantage of these Permian rocks. And you can see an outcrop there. You can see some crystalline rocks there.
What did you call those? Grape arbors?
Oh, grape arbors? Yeah,
Some of them
biology. Yeah, this is biology, not geology. So So the Permian rocks, you can see them here, you can see how red they are, but a lot of it's mainly covered, but there's several thousand feet of this Permian. Let's go to this one. So here's the basement rock, here's the Permian fill, again 3 kilometers thick. And then at the end of all of that, once the structural complications have ended, we see sediments being shed off of the mountains to the northwest during late Permian time, out towards the ocean, and it's the Val Gardena sandstone and what's called the Bellerophon Formation. Bellerophon, the name, it's a genus of snail that's planisphyrally coiled, and they can, be fairly large size. Here's the Bellerophon Formation. So here are some Permian red beds and carbonates, so it's sort of an interfingering of fluvial, deltaic, tidal flat with shallow marine. So you get these alternations of different colors and different lithologies. So again, subsidence, lots of sediment being shed in, but predominantly tidal flat and marine. That's this stuff. Then there's a regional unconformity, and the first deposits of Triassic age sort of continue with that same motif. So here's the Bellerophon Formation. Here's the Permian-Triassic extinction event. And you go into the Werfen Formation, and you can see how thick the beds of the Werfen Formation are, a couple thousand feet. Again, sort of the same thing, some marine, non-marine, marginal marine. And it's been broken up into a number of members here. So here's the upper part of the size member here. That is equivalent to the black dragon member of the Moenkopi. And the gastropodon oolith is a high stand carbonate deposit that is equivalent to the Sinbad limestone out in the San Rafael Swell. Again, this is all sort of the pedestal that really the good stuff we're getting to is built on. So here's the Werfen Formation again, and as you get to the top of it, there's an unconformity in a big thick conglomerate called the Richthofen, named after a geologist there. But the Scythian here, this is the early Permian. Then you go into the middle Permian, which is the Anisian. Here's the Bellerophon and the Werfen Formation one more time, and then peeking over the hill, the good stuff yet to come. Okay, so I think all of us would feel pretty at home in these kind of sediments. These are things that you've probably seen before. But then, once that pedestal has been built, that framework has been built, we now start to see the real buildup that the Dolomites are famous for. And in the middle Triassic, which is the Anisian and Ladinian, we see the first marine beds coming in, big, huge carbonate isolated platforms, and then we fill all of that relief in with another slug of volcanics. So just as background, carbonates form different types of platforms. They can be on a wide ramp, they can be on a rim shelf, such as the Great Barrier Reef, or they can form as isolated platforms. And examples, so here's an isolated carbonate platform surrounded by deep water on all sides. Here's the best example from the modern day, the Bahama platform, separated from Florida by the Straits of Florida. Or we could go down to Belize, and we find these atoll-like isolated platforms. And it's interesting that these isolated platforms form on rift faults down in the ocean floor. We see a similar thing in the Dolomites to a degree. So here again, Google Earth view or Google Maps view of the Dolomites with these beautiful lush valleys and these high bare limestone edifices. These are isolated platforms. Back during Triassic time, take away some compression, later tectonics. These would have been isolated platforms, and this was the deep water between them. So let's take a look at, there's a number of names that you'll see in guidebooks for this carbonate in here. The Marmolota, the Latimer, the Rosengarten, the Schlern, but they're all the same, this middle Gneissian to Ladinian, middle Triassic carbonate buildup. So this is one of the localities that we went to. Yeah. So this is the Werfen Formation down here. This is a cliff of the Contrin, which is the first major carbonate deposit. Then here's some deep water deposits, and then above that, these Ladinian buildups. So here's the Contrin. Here are these relatively deep water living Longo beds, and then above that we get these big isolated platforms developing. Here's one of them called the Schlern, the Schiller and Schlern. So it has a pedestal of Contrin and those other formations. These are all the Permian red beds, the Triassic fill, but then bam, we have this big, huge carbonate buildup. Colin?
So has there been any karst deposit in these at all, or is it separated between isolated carbonate platforms?
Yeah, the separation is all depositional. Yeah. And then you can see the next isolated platform over here. You can see another one lurking back here. So just think of this as sort of a fish's eye view of the Bahama, modern day Bahama platform, where water would have been up to here, and then all this stuff's being shed off. I'll show you the evidence of that going forward.
Going back there, if you were one of the early geologists that mapped this area, how would you know these were isolated platforms and just not erosional remnants? How long did it take them to switch on the light bulb?
Let me show you with the next slide. It actually came pretty quickly because, so here's the Contrin, the first limestone that sort of, then that got faulted, and these faults nucleated, sort of like we see the atolls in Belize, started nucleating carbonate buildup, and then those continued to build. Sometimes they fractured, and you get these big, huge Neptunian dikes. And then deposition continued. So in here you have nice lagoonal, laminated, flat-bedded limestone carbonates, but adjacent to it you have the steeply sloping four-reef beds in all directions. So it sort of tells you that this is an isolated entity. Not to say it didn't take a lot of effort, to piece it together, but as far back as 1761, they really had a pretty good handle on the modern stratigraphy. Yeah, these were good geologists. But so you can see these platforms build, and then they shed. So you have four reef beds, you have big blocks of reef rock and things tumbling down the cliffs. And if we take this shot, here's the Contrin beds at the base, but here are the four reef beds, and then way back up there in purple are the flat-lying beds. And you just see them transition one right into the other, but on a huge scale. It takes a lot of effort to climb up through all those gullies and all those cliffs to see all that up close and personal. Okay, so I think we're changing gears here. Let's jump into, okay, so we're back into this area. And now I want to take you to, here's the Rosengarten Reef. I want to take you to the Latimer Reef, or Latimer isolated platform. These are all deeply eroded, so that adds to the complexity of not by karst, but just valley and glaciation, whatever. So here's the Latimer buildup. It's rimmed by a reef, flanked by debris beds, and then the lagoon and reef beds on top. And if we do a cross section, here are the lagoonal rocks, here are the reef rocks, here are the floor slope rocks. So again, you can just walk across there, do careful observations, careful collecting, and piece together the paleogeography. Let's take a look at the interior first, the lagoon. So here is the Latimer buildup. the core of this big chunk of limestone or dolomite. Look how well bedded that is. So people have studied these to a fairly well. And here's the 1991 paper. And Linda Heinhoff was here last semester giving a talk over in engineering, if anybody went to that. So the Middle Triassic ladder limestone, the Dolomites, consists of hundreds of vertically stacked meter-scale platform carbonate cycles. Each is composed of a shallow marine subtidal unit with a thin vadose diagenetic cap. These so-called Latimer couplets are products of repeated episodes of sea level change over 20,000 years. Couplets arranged in upward thin bundles of 5, indicating the presence of a 100,000-year modulating component. So Doc Morris would love this because we can use the M word there, Milankovitch. But these are lagoon, center of the isolated platform center lagoon deposits that are controlled by climatically induced sea level oscillations. And here they are, closer up. When you get to the edge of the platform, these are equivalent age limestones, but look at the cross-bedding in there and look at the scale of that. So here are again, this sort of Contrin beds, and then here's the buildup of Ladinian age, and you can see how far these things prograded. If we look at the reef beds, we can see some corals. And remember, there are a lot of corals, or there are corals in the Permian. Nobody's ever found any early Permian corals yet. So they really got clobbered at the Permian-Triassic extinction. No genus that we know of got through. But by the time you get to Middle Triassic, we see corals, not rugose or tabulate, but now scleractinian corals, a totally different order of corals, show up and start to build reefs again and play an important part in some of these reefs. Lots of post-extinction foraminifera. The Europeans, especially the Germans and Austrians, love their calcareous algae. So if you're interested in calcareous algae, you can find all the papers you want, okay? And bring them on the trip, carry them in your suitcase. In fact, bring a suitcase just for that and annoy everybody with your knowledge of calcareous algae, okay? Actually, they're kind of cool. Yeah. How about sponges for dinner? So there are calcareous sponges. There are these encrusting types of things. So lots of interesting types of critters within the reef rocks in those Ladinian or Middle Triassic limestones. And then, again, this just shows the complexity of rocks. Here are the embedded inner platform. Here are the slope deposits. Here are the breccias down at the toe of the slope. Here are the beds that it was built on top of. So a lot of complexity, but a lot of cool things to discover there. So that's these buildups of Ladinian age. Then the whole carbonate thing sort of fell apart. We're not sure if it was tensional tectonics. Usually when you get faulting and you get a lot of volcanics and basalts, you think of rifting, but there's some evidence now that there may have been some compressional tectonics in Middle Triassic. Regardless of what the cause, carbonate deposition ceased, and all of there's thousands of feet of relief in between these isolated platforms filled with volcanics and volcaniclastics. So something was going on over there in the Tethys tectonically to go from beautiful carbonate deposition to the schistoclastics.
We were moving a little more quickly. We moved them. I'm just saying, volcanic. You see them today in abundance.
They have eroded much more readily than the carbonates. But here's a diagram that shows that. So here are these big carbonate platforms now rifted or structurally modified with dikes running up through it, volcanic dikes, and then just any relief that was left was filled with volcanics and with volcaniclastics. So here's sort of a cartoon showing the Ladinian isolated platforms. Then they get fractured and faulted. Subaerially formed lavas up here. volcaniclastic deposits and pillow lavas down in here, so some volcanic activity submarine. Here you can see through these carbonates, you can see these dikes, volcanic dikes running through, or igneous dikes running through them. Here is the next big buildup of carbonates, but they form on top of this volcaniclastic fill. And in these areas down here, a lot of the fill looks like this, where there are big chunks of Permian and earlier Triassic formations, volcanic material, chunks of the reef just getting shed off and eroded into the sump, filling up that relief. This is sort of a cool photo. So here are the Ladinian Middle Triassic reefs. And here's relief. Look at the volcanics and volcaniclastics just lapping onto it and filling up the topography that was in between. And then you can see the next generation of carbonates there in the upper right. So that's the Middle Triassic. And in Utah, again, we have no Middle Triassic whatsoever, but all of that good stuff is happening over there up at the head of the Tethys embayment. So here are all the names that go along with that. At the end of that, we'd filled in the basin again, and on some irregularities or perhaps little structural highs and lows, we see the development of the next set of isolated platforms that belong to the Cashin and the San Casino formations. So I'll show you what those look like. These. So now to illustrate that, let's go to the Sella Massif. And this is what, if you're going to go to the Dolomites, other than this trip, you need to go to the Sella Massif. I mean, it's sort of quintessential Dolomites. And what's cool is there's a road you can just drive all the way around it, go through 4 high passes as you circle that isolated carbonate platform. So here's what it looks like. Here are the passes. You can go around the whole thing. And here's what it looks like. Again, fish's eye view of this isolated carbonate platform. And you can see the relationships. The SC and the DC, the sand Cashin beds and the Cashin beds. We see the carbonates up here. We see basinal deposit. We see this intertonguing. Again, you can see the progradation of these isolated platforms out into and over basinal deposits. And just to show that a little differently, so here's the San Cassiano basinal deposits, the shelf and slope Cashin deposits, dolomite. And here's that generation of platforms. So these are younger than the ones we looked at previously. These are full-grown pine trees for scale. I don't know what that helicopter was doing, if it was headed off to a rescue or something, but flew over at just an opportune time. We're looking at a 2,000-foot wall here, and it's all dolomite. On top of it is the next package. These are red beds of the rival formation, and then up here, sort of a capping thing called the Dolomio Principal, or the principal dolomite. But let's look at the Cashin beds here and the San Casino here. And so if we take that and turn it into a cartoon, these are basinal deposits. This is limestone, but it's all slope deposits. You can see the inclined bedding here. So let me back that out. So these are basinal deposits. And if you follow one timeline, you go from the basin and a 35-degree angle up a 2,000-foot slope, 2,000-foot high slope, up to the reef and up to the top of the platform.
To really do this justice, you have to do that finer. You have to find each phase separately, just to really understand it. Is that right?
That's right. Yeah. Yeah. Isn't that impressive? I mean, just think of, on a timeline, going from the basin and then scuba diving up along that long slope before you get out on dry ground. I mean, that's just a huge submarine surface. And it prograded, in a million years, there was 2 kilometers of lateral progradation. How much sediment production do you have to build something 500 meters high and have it prograde 2 kilometers? That's a lot of sediment production in shedding. Okay? So there's, again, the 35-degree inclination. And the thing that's interesting is, there are different types of carbonate factories, tropical, which we think of the Bahamas, cool water that you may not be that familiar with, but in this case, microbes are important. So here's that 2,000-foot high thing. Here are the 35-degree slopes. Here are the black basinal units. Here are the conglomerates at the toe of that long slope. And if we take a look at rock carbonates from here, I just want to have you look at this right bar. These are microbial carbonate muds. Very little at the toe of the slope. But up here on the slope itself, the dominant material is microbially induced mud precipitation. And then you get some of that up on top of the platform as well. Here's what that stuff looks like. I mean, it's sort of, you look at it in a thin section, it looks sort of like clotted mud with some sparry calcite. Here's some microbial things binding the cement and growing on, and cement growing on it. But sort of a weird type of limestone. It's not the big corals. It's not some of those other things, but huge amounts of mud. And we don't need to go into all that. But so down towards the toe of that slope, again, these are full-grown pine trees. These are boulders. These are boulders of reef rock from 2,000 feet up at the top of that slope that have come down chaotically and precipitously down that slope. These are referred to by the locals over there as the Sipit boulders, C-I-P-I-T. So these are house-sized boulders that have accumulated down at the toe of this carbonate slope. If we could dry up the Bahamas and go to the toe of the slope there, we'd see lots of stuff like that. Yeah, it's pretty common. We'll see it in the Guadalupe Mountains, or some of us will see it in the Guadalupe Mountains towards the end.
Earthquakes to dislodge them, and just happen naturally.
Can happen by just over-steepening and just overproduction of sediment, or earthquakes as well. We know it's tectonically active areas, so it could be. Here's another outcrop of a bunch of toe slope boulders. These are more that size, but it's just a pile of carbonate boulders, and a lot of these are shallow water critters, but we're down here in fairly deep water. And here are the laterally equivalent beds. So here you can see the big cliffs up here, but this is the deep water stuff down at the base of this is the ocean floor deposition, which forms a halo around, or the area in between these carbonate buildups. So it looks like good deep water deposits, done at thin-bedded, dark. Those might be distal turbidites, or they might be some sand lenses or whatever. But yeah, but this is black shale deep water stuff. So that's these beds, and then a low stand of the sea, and you get these red beds called the rival beds. Then you develop, at that point, the individual carbonate platforms have more or less coalesced and disappeared, and you get this broad deposition of dolomite called the Alpdolomite if you're German, or the Dolomio Principal. Then on top of that, some beds that are called the Dachstein beds that you'll probably see up near where did they film The Sound of Music? Yeah, so maybe up that way, up towards Wolfgangsee and St. Gilgen. So here are the St. Cashin beds, again, the rival beds, and then the last one that I'll show you, this is that principal dolomite, or this sort of area capping widely dispersed carbonate platform, which is pretty cool in and of its own right, although they're fairly well eroded. Then, on top of that, you finally get into some Jurassic sediments. And this is what is known as these beds are called the Amanitico Rosso. Rosso meaning red, Amanitico meaning ammonoids. So you can see the ammonites there. You can see the red color. You can see it here. I don't know where you're going to see. Are you going to see these up near Salzburg? Yeah, I think there's some localities. It's fairly widespread around the Tethyan realm or the southern Mediterranean, Italy and Austria. Here are some more. This is fairly typical. It's almost like a red chalk. This is a deep marine deposit. It's got coccoliths. It's got small forams. It has pelagic ammonoids that have settled down in it. It's red because the seafloor at the time was oxygenated. So these are not terrestrial red beds, but these are deep marine red beds. And here you can see the blotchy carbonate. Again, you can see the ammonites that give it its name. And these formed after the Triassic had had its moment. During the Jurassic, area started undergoing rifting. And the seafloor, it subsided, had this faulted seafloor and relatively deep water deposition across that are these so-called Jurassic red beds. Here you can see sort of a conceptual representation of the rifted, faulted surface or seafloor, and then the Amanitico Rosso forming in these half grabens. Okay. And that's all I have. I think that's so Dolomites and Amanitico Rosso. But anyway, a fairly complex area, but absolutely beautiful. And any geology, anything you learn there, or that people have learned, they have earned because of just the high relief and the topography and the access. It really wasn't until fairly recently, 150 years ago, that it was really easy to travel across. There were trade routes through there. There were military routes through the Dolomites, but just for the average tourist or average person getting there was pretty tough going. But
you get a copy of their PowerPoint and print out these photos that they can.
Yes, absolutely. And I think Bob Lindsay has a really nice guidebook that I think that goes through a lot of that as well. I mean, there are guidebooks available. It's just I wasn't sure how much time you were going to spend there and really how much detail to go into. But anyway, so if that's too much, too bad. If it's too little, yes, thank you.
You know 100% more about Dolomites than I did before.
Okay. Okay.
Are you coming with us?
No, because I wanted to spend the whole week there. And Jeff said no, so I threw a tantrum.
The red ammonite beds, so they were deposited in the seafloor was oxygenated. Why was that?
Just because of circulation. So in the modern world, there are bottom waters are oxygenated more than the water column, just because you have descending surface currents that carry oxygen down across, though. Yeah, it's pretty. I mean, it's sort of unique to see, red beds in relatively deep marine, but the lithology and everything else tells us, and the setting tells you that it's deep water.
Other questions? So are you going to go see those overnight things? Yes, you can buy them in the gift shop at home. Lots of them.
Those are
They're manufactured in China.
Yeah, how much can you fit on the airplane, right?
We'll see what we can do.
Happy birthday, Bonnie.
Oh,
They sang happy birthday. So, okay, yeah. So I don't know if Bob Lindsay is listening in remotely today. He's probably turning over in his grave. He'll correct everything that I got wrong. Okay. Turning over on his sofa or something. All right. Well, thank you guys. Appreciate it. I guess I better. Pull something. I don't know if I'll go for an hour, but I'll at least cover the talk about it.
Show a few YouTube videos or something.
Okay, yeah, I'll bring some.
Thank you.
So I don't know if you want these to take
Yes.
other people or.
I'll put them in the folder.
But I'll
We'll
give.
probably print out the whole PowerPoint
Okay.
and put it in the book.
Okay. All right. Then I'll clean our notes.
Forestry personality.
Thank you so much.
Uh huh.